The day the EMD 567 roared to life, American railroads began an irreversible transformation. Suddenly, every revolution of the crankshaft delivered power where steam had wasted energy and time. Mechanics couldn't believe what they saw. A compact V16 packed more force, easier maintenance, and a sound that would become legend. How did one radical engine topple an entire industry, and why are its secrets still misunderstood today? Tap like to help more rail fans discover the truth behind this revolution. Inside the EMD 567, every movement of air and metal was carefully orchestrated to do more work in less space than any locomotive engine before it. The heart of this design was the two-stroke cycle, a system where each piston delivered a power stroke with every single turn of the crankshaft. Unlike four-stroke engines, which require 2 revolutions for 1 burst of power, the 567 cylinders fired twice as often, packing more energy into every revolution. Fresh air entered through ports cut directly into the cylinder liner, rushing in as the piston dropped. At the top of the cylinder, poppet valves opened with precise timing to let spent exhaust escape. This uniflow scavenging sent air and exhaust in a single, continuous direction, clearing the way for the next charge and making combustion cleaner and more complete. The result was an engine that did not just breathe, it inhaled and exhaled in a rhythm tuned for relentless, high-output work. This firing pattern was not just a technical curiosity. It meant that a compact V16 could deliver a steady, almost unbroken stream of power, crucial for pulling heavy freight across long distances. The relentless cadence of the two-stroke cycle set the EMD 567 apart, giving it the responsiveness and muscle railroads needed to move America forward. 8.5 inches across, 10 inches from top to bottom, that's the bore and stroke that gave the EMD 567 its name. Each cylinder displaced exactly 567 cubic inches, and with 12 or 16 cylinders lined up in a 45-degree V configuration, the total swept volume reached 6,804 cubic inches or 9,072 cubic inches. This compact V configuration was not just a packaging trick, it allowed designers to fit immense power into a surprisingly short engine bay, making the most of every inch inside a locomotive's car body. But size alone was not enough. The real secret was how the engine moved air. Instead of relying on exhaust-driven turbochargers, the 567 used a mechanically driven roots blower, a gear-driven pump spinning at about twice the speed of the crankshaft. Even at idle, the blower forced fresh air into the cylinders and cleared out exhaust, guaranteeing a full charge no matter the revolutions per minute. Each revolution of the crankshaft sent the blower's lobes whirring, packing the air that swept through the liner ports as the pistons dropped. This constant pressurized AR flow kept combustion clean and forceful, supporting the relentless firing pace that defined the 567's output. With every dimension and every turn, the engine's breathing was engineered for maximum effect. No wasted space, no wasted motion, just pure, dependable power. Fuel delivery in the EMD 567 relied on a system that was both simple and robust. Each cylinder carried its own unit injector, a compact module that combined high-pressure pump and nozzle in a single body mounted directly in the head. Driven by the camshaft at crankshaft speed, these injectors delivered precise bursts of fuel with every revolution, matching the relentless rhythm of the two-stroke cycle. There were no long, vulnerable high-pressure lines to fail or leak. Every pulse of fuel arrived exactly when and where it was needed, even when the engine ran for days at a steady 800 revolutions per minute. Beneath the block, a massive forged steel crankshaft absorbed the pounding of thousands of power strokes per minute. The crankcase itself was cast from a high-strength iron alloy, designed to resist flexing and cracking under constant load. Cylinder liners, known as wet liners, stood in direct contact with coolant, carrying away heat and making replacement straightforward. Pistons used a two-piece design, a steel crown to handle the searing combustion, and an aluminum skirt to keep weight down and reduce friction. Every material and mechanism was chosen for a single purpose: to keep the engine running strong mile after mile, shift after shift. The result was a prime mover that could handle the punishing duty cycles of American freight railroading, laying the foundation for a new era of reliability before the first wrench ever turned in a maintenance bay. In a diesel shop, the difference between a train moving freight and one sitting idle often came down to a single decision: how fast could a bad cylinder be replaced? With EMD 567, the answer was measured in hours, not days. Mechanics did not have to strip down the entire engine. Instead, they used an overhead crane to lift out a complete power assembly, including liner, head, piston, rod, and carrier as one unit. On a typical afternoon, a crew could swap out a failed assembly in as little as 2 to 6 hours, depending on experience and shop layout. Compare that to the multi-day ordeal of steam engine repairs, where boiler work or running gear fixes could tie up a stall for half a week. This approach changed the rhythm of railroad maintenance. Instead of waiting for a lengthy teardown, shops kept rebuilt power assemblies on hand, ready to drop into any locomotive that rolled in with a problem. The process was so streamlined that a locomotive could arrive in the morning and leave under its own power by the end of the shift. Mechanics learned these techniques at EMD's own training schools, where classrooms were filled with cutaway engines and full-size mock-ups. There, new hires practiced every step, including rigging, torquing, and injector timing, under the guidance of instructors who had worked on the real thing. The result was a workforce trained not just to fix engines, but to keep entire fleets rolling with minimal downtime, saving railroads both money and lost miles. Across America, the EMD 567 did not just power one kind of train, it became the muscle behind an entire generation of locomotives, each designed to tackle a different job. The road switchers, starting with GP7 in 1949, brought 1,500 horsepower to mainline and branch line service, blending the pulling strength of a freight engine with the flexibility to handle yard work. The GP9, introduced in 1954, pushed that figure to 1,750 horsepower, and its reliability kept thousands in service for decades. In the yards, switchers like SW7, SW9, and SW1200 ran almost non-stop. Their 12-cylinder, 567 engines handled low-speed starts, stops, and long idle periods without fouling, a feat that left many four-stroke rivals struggling. For passenger service, E-units like E7, E8, and E9 carried twin V12 567 engines, each engine driving its own generator. With a combined output up to 2,400 horsepower, these locomotives could keep long trains moving at speeds near 100 miles per hour. If one engine failed, the other kept the train rolling, a built-in redundancy that mattered on tight schedules. Diesel-electric traction changed how power reached the rails. The 567's constant RPM fed direct current generators, which supplied traction motors with smooth, controlled torque. Engineers could dial in just the right amount of pull, from a dead stop to full speed, or use dynamic braking on steep grades to slow heavy trains without wearing out the brake shoes. This was not just a new engine, it was a new way of running a railroad, and railroads responded by ordering entire fleets. The sound of the 567 became the soundtrack of American freight, passenger, and yard operations from coast to coast. As the EMD 567 spread across the continent, the transformation rippled far beyond engine rooms and shop floors. Steam-era roundhouses, once the heart of railroad towns, emptied out. Their stalls and turntables left idle as diesel locomotives needed less frequent and less specialized care. Coaling towers, water tanks, and ash pits were dismantled or left to rust. Maintenance crews that once swelled with boilermakers and firemen saw their roles shrink or vanish, while a new generation of mechanics learned to read manuals and swap out modular assemblies. The shift did not just change machines, it redrew the rail industry's entire map of labor, logistics, and infrastructure. The story of the 567 did not end with its last day on the assembly line. As original parts wore out, railroads turned to retrofit kits, fitting later model 645 series power assemblies into aging 567 C and D crankcases. This quiet upgrade extended the working life of thousands of locomotives, letting fleets run on with a blend of old iron and new technology. Engines that once hauled mainline freights found second lives on branch lines, in switching yards, and in industrial plants. Others moved into tugboats, sawmills, and backup power stations, where their steady output and easy service made them favorites in demanding settings far from the rails. Today, the legacy endures in the hands of volunteers and preservation crews who keep 567 powered locomotives alive for museums and tourist lines. Many of these engines still run with a mix of original and upgraded parts, their sound unchanged since the 1930s. The same design that once rewired an industry now sustains a living connection to the past, proof that durability and adaptability can outlast even the boldest revolutions. Even now, thousands of locomotives still echo with the signature pulse of the 567's design. In an era chasing automation and efficiency, its legacy raises a question: how long should we expect true innovation to endure? Sometimes, the future still runs on yesterday's best ideas. Thanks for watching.